Hello students, welcome to the class. Today we will see the NCERT chapter 3, classification of elements and periodicity in properties theory part 5, in which we will cover section 3.7. This is the disclaimer. In this lecture, you will be seeing the periodic traits in physical and chemical properties of the elements. Then we will try to develop a relationship between ionization enthalpy and metallic character. And lastly, we will see the scientific vocabulary appropriate to communicate ideas related to certain important properties of the atoms. Example, atomic ionic radii, ionization enthalpy, electron gain enthalpy, electronegativity, and valence of elements. If I talk about the subpoints, so our focus would be on periodic trends in properties of elements. Then we will see trends in physical properties and the problems related to 3.5 and 3.6. Now, a very important point, that what are periodic trends? So this is very important to understand. You can think of periodic trends as an observable patterns. So when you will move across the periodic table, you will observe a pattern in both the physical and chemical properties. So the periodic trends related to physical properties are called as periodic trends in physical properties, whereas the other one is called as periodic trends in chemical properties. Okay, so trend basically means patterns here. The physical properties whose trends we are going to discuss today will be atomic radius, ionic radius, and ionization enthalpy. We will deal with this electron gain enthalpy and electronegativity in the upcoming classes. Now, this pattern is seen both horizontally and vertically. So it can be observed on descending down the group and on moving across a period. So we will see the trend in both the verticals. Okay, so in vertical sense and horizontal sense, we will see the periodic trends. Now, if I talk about some of the example of periodic trend, then you can think of chemical reactivity. On moving from group 1 to the middle of the periodic table, the chemical reactivity decreases. Means, so this is just an example for the pattern which I have told you just now, that there is a pattern in the chemical reactivity and the physical properties. So one such pattern is given here. Chemical reactivity decreases if we move from group 1 to the middle, and then it increases to a maximum of the group 16. Okay, so we can say that the group 1 elements are the most reactive one among the metals, because in the left half of the periodic table we have our metals. So the alkali metal and the alkaline earth metals will be the most reactive one. Now this reactivity goes on decreasing, and after a middle point it starts to increase. So we will discuss about that middle point when we will discuss the periodic trends in chemical properties. Now this chemical reactivity increases to a maximum of group 17, means the halogen. So among the non-metals, the halogens is the most reactive one, and among the metals, the alkaline and the alkali earth metals are the most reactive ones. Now moving on to the atomic radius. So this is the first physical property that we will discuss today. Now, if I talk about the atomic radius, then it is very difficult to determine the atomic radius of any given element. The reason behind it is that, first of all, the radius is very small. Okay, it is not big to measure it physically, so that is very difficult. And second point is that we have learnt about the probability density, means we are unaware about where the electron is present exactly. Okay, so as a result of this, we cannot define a definite boundary of the atom. So again, I am repeating it. The first point is that the size of the atom is very small. The second point is that we always describe the probability of finding an electron. Therefore, we cannot define the boundary of the atom. So that creates a problem in knowing the actual atomic radius of any atom. Now, what is the solution to that? The solution to that is to consider the combined state. Combined state means it is, I would say, bonded to any other atom. So that can be of two types. If we are considering for non-metals, if we are considering the atomic radius of the non-metals, then we do consider their covalent radius, and for the metals, we consider metallic radius as the atomic radius. Again, I am repeating it. For the non-metals, we consider covalent radius as the atomic radius, and for the metals, we consider metallic radius as the atomic radius. I guess this part is clear to you. Now, we will try to define both covalent radius and metallic radius separately. So, what is covalent radius? It is half the distance between the nuclei of two identical non-metals. So, this point is very, very important. In case of covalent radius, we take those non-metals which are identical, means same, and then we calculate the distance between their nuclei and just half it to get the atomic radius. For example, suppose you have to calculate the atomic radius of chlorine. Now, as I have told you, it is very difficult to calculate the absolute atomic radius of chlorine because of its small size and of its undefined boundary. Then what we will do? We will take the Cl2 molecule, which is the molecule of two identical nonmetals, that is chlorine, and calculate the bond distance, which is distance between their nuclei. Suppose it comes out to be 198 picometer. So this is the distance between two nuclei which are covalently bonded in case of chlorine molecule. Just half that distance, which is 198 by 2, you will get your atomic radius for the chlorine or the covalent radius for the chlorine. So in case of non-metals, both terms can be used, right? I guess this part is clear. So this gives you 99 picometer as the covalent radius of the chlorine. Now what about the metallic radius? In case of metallic radius, we take the metallic lattice. So if you take iron metal, then it consists a lot of atoms of iron present inside it. Just take any two adjacent metal atoms. So this part is very important. Two adjacent metal atoms. Those metals should be present adjacent to each other. Adjacent means just after one another. Now take the distance between the two nuclei and half it to give the metallic radius of the metal or the atomic radius of the metal. Now by metallic lattice we mean that suppose you are taking the iron metal, right? That iron metal on the molecular level is built up of a close compact 3D structure. So that is referred to as the metallic lattice. In simple, you can think of it as a way. Suppose you are taking a metal surface of iron and you are taking two iron atoms which are close to each other or they are in contact to each other. Just calculate the distance between their nuclei and half that distance and you will get your atomic radius. Suppose we take the example of copper atom. So the distance between two adjacent copper atoms is found to be 256 picometer, and to calculate the atomic radius of the copper, or you can say the metallic radius of the copper in case of metals, it will be 256 by 2, 128 picometer. So this is taken for copper because Copper is a metal. Remember this point, this is very, very important. Now, how are we determining the distance between two adjacent copper atom, or how are we determining the distance between the two chlorine atoms that are bonded to each other in the case of non-metals? For that, we use the X-ray or spectroscopic method. So this is experimental and this value will be given in your question, right? If it is asked to calculate the atomic radius, the value will be given in your question. So this X-ray spectroscopic method and other spectroscopic method like your IR is also used, but that is used for a different purpose. So these are used to calculate your both metallic and covalent radius. Now we will see the trend that is related to the atomic radius for the periods. The first point is that the atomic size decreases across a period. So as you move from left to right in a period, the atomic size decreases. What is the reason behind it? So when you are moving from left to right, you are adding the electron to the same energy level. This increases the effective nuclear charge on your nucleus as a result, on the energy level, and as a result the shell experiences a greater attraction force towards the nucleus, right? And this decreases the size across the period. So let us try to imagine it with the help of a pictorial representation. Now this is the diagram that will help you to understand this thing. Suppose you are taking three elements of the same period, which is lithium, beryllium and boron. Now in case of lithium, you would see that on the outermost shell only one electron is present, and that is getting a force from the center, which is your proton. But as we move to the beryllium, your same shell is having two electrons. You can see it, they are present on the opposite sides. Now your same shell, which is your second shell, I would say, is experiencing a double force because two electrons are there and both are attracted because of the electrostatic force of attraction from the proton in the middle, right? This is clear. Now we add a third electron onto the same shell. This creates more force on the outermost shell and your atomic radii decreases. This is clear to you, I guess, how the size is decreasing because of the increase of electron on the same shell, and that is increasing the effective nuclear charge on the same shell. Now do not consider the shell which is enclosing your positive charge as your shell. So this is indicating the nucleus. After that, where you see an electron in the light gray color, so that is indicating your first shell, and after that we have the second shell, we have the electron as the dark gray shell, right? And you can also see the increase in the electrons. So the first lithium has electronic configuration of 1s2 2s1, then beryllium has of 1s2 2s2, and boron has a 1s2 2s2 and 2p1. So the electron is increasing one by one because of the increasing atomic number across a period. So this was the trend across period. Now there is a table to illustrate the same. First of all, this is your graph. So this graph is for the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So as you are moving from left to right, the atomic radius is decreasing. You can see it very clearly through the graph. So this graph is showing the variation of atomic radius with atomic number across the second period. This is your second period. Now the same can be seen in the table. Lithium has a atomic radius of 152. Okay. Then beryllium has atomic radius of 111. Then boron has of 88, 77, 74, 66 and 64. Similarly, for the third period, you can also observe the same trend. 186, 160, 143, 117, 110, 104 and 99. Now all of this is showing clearly that as we move from left to right in a period, the atomic radius decreases, and that is happening due to increased number of electrons in the same shell that increases the effective nuclear charge. Now let us look at the trend that we see in a group. We have seen it for the period, now we'll see it for the group. If I talk about the trend in one line, then I would say that the atomic radius increases down a group. Now there are exceptions to it, but we will not talk about them now. We'll talk about them in the upcoming classes where we'll see the S and P block. But for now, you should remember that the atomic radius decreases down a group in general, and the reason behind it is that as you are moving down the group, the number of shell is increasing. Okay, the number of shell is increasing, and that is increasing the size of your atom. So this can be shown again by the pictorial representation. Now here is one more important point. You would say, okay, the number of shell is increasing, but at the same time, the number of protons is also increasing. So the outermost electron must be experiencing the force due to increased number of protons as we move down the group. But the problem is here is that with increasing shells, more electrons are present inside the shell. So this is shown in the trapezium box. Okay. Suppose this is the first shell, second shell has 2 electrons, then the third shell. Now, the 2 shells which are present in the trapezium box, it is showing that these 2 shells are shielding the valence electrons. As a result, the increasing number of proton is being outweighed by the shielding effect. Outweighed means it is being nullified by the increasing protons. I guess this point is clear to you. The same thing is written here. The principal quantum number increases, positioning the valence electron away from the nucleus, right? And the second point is that although the positive charge is increasing on the center, but more and more electrons are present in between the nucleus and the valence electron, that increases the shielding effect. Now we will see the plot for the same. So this is the plot for 2 different groups. You can see that from lithium to sodium, the size is increasing, and then it keeps on increasing to potassium, rubidium and cesium. 152 picometer, 186 picometer, 231 picometer, 244 and 262. Similarly, if you look for the 17 group, there also as we move down the group, the atomic radius is increasing, and there is no anomaly or no exception in it. So 72, 99, 114 and 133 picometer. So we can imagine the same in the table. You can see in the table that as we are moving from lithium to cesium, the atomic radius is decreasing. Similarly, if you are moving from fluorine to the acetine, the atomic radius is increasing, and that is happening due to increased number of shells on the outermost area, right? So we have seen the atomic radius, we have seen its trend right now, and we have also justified the reason. Now we will move to the exception part. So this I would say measure of calculating the atomic radius in the combined state. Remember, we are calculating the atomic radius in terms of combined state. This is not applicable to the noble gas. Noble gas is an exception to this methodology. What is the reason behind it? Anyone who can say it? What is the reason behind it? That you can't use them in the combined state, or they do not exist in the combined state for the noble gases, right? So we have seen for the metals, we can't use, for the metals we were using the metallic radius. For the non-metals we are using the covalent radius, but for the noble gas we can't use the combined state. Yes, the answer would be that they have a zero valency. Very good. Means they cannot be in a combined state due to their complete electronic configuration of 8 outermost shell. And due to this reason, we take their radii in the non-bonded state. Now that is done with really sophisticated machines, and of course, since they are in the non-combined state, therefore their radii will be exceptionally large, because in the combined state your two, I would say, atoms come closer to each other, therefore the actual size of the atoms gets reduced. But if you take the noble gas, and since they are present in the non-combined state, their isolated radius is very large, and hence we can't use this trend onto the noble gases. Now for monoatomic elements, we use a third type of radius apart from the covalent and metallic. We will discuss about it in the upcoming classes, where we will see it in the chemical bonding. So that thing is called as van der Waals radii. Okay, I'm not discussing about it right now. We'll see it in the chemical bonding. But remember, for the case of noble gas, we do not take the covalent radius, neither we take the metallic radius, we take the van der Waals radius. Now this van der Waals radius is applicable onto both metals, non-metals and noble gas. We will see onto it what does it mean. But for now, remember this point. This is very, very important. Okay. Now moving on further. The second physical property which we will see is the ionic radius. Now there are some general points you must know. Ions are of two types, cations and anions. How are cations formed? They are formed by the removal of electrons, due to which they develop positive charge. Now a very important point, that your cation will be always smaller than the parent atom. We can take the example of sodium, which has an atomic radius of 186 picometer in the neutral state, but in case of the ionic state, it has a ionic radius of 95 picometer. You can see how large difference is being created by removing just one electron. So why it is happening? Because the number of proton is not changing, but the number of electron has been reduced. Now the same number of proton are applying a greater amount of force on a lesser number of electrons. As a result, the radius contracts. This can be understood with the help of this diagram. You can see that your sodium has a 11 electron configuration. If you remove one electron, then the sodium acquires a positive charge due to one extra proton, and that extra proton exerts more force on the remaining electrons, and as a result you would see that the size contracts. So you can think of it with the example of tug of war. Suppose on both sides 5 people are pulling the rope, right? And there is a balance of force. The rope is not being adjusted to any of the side. Now what I do? From one of the side, I remove one person. Suppose now there are 4 persons on the right side and 5 persons on the left side. What will happen? On the right side group, it will be dragged towards the 5 side group, and the right side group will lose. Why it will lose? Because more pressure is been created by those 5 persons. Similarly here, the protons count is same, but you have removed the electron. As a result, they will be I would say dragged towards the nucleus, and hence its size is decreased. I guess this point is clear to you, why the actual atom has a greater size as compared to the cation. Okay. Now next, we will move on to the anion. Now what are anion? Anions are formed by the addition of electron, due to which they will acquire a negative charge because there are greater number of electrons. Why it is happening? So the reason is that as you introduce one more electron, there is a repulsion between the electrons. Now, first there is a repulsion, and second, there are lesser number of protons present at the nucleus as compared to the electrons. Hence, each of the electron will experience a lesser amount of force, and hence they will expand out. So this can be shown in this diagram. Your chlorine, which initially has 5 electrons in the outermost shell, after gaining one more electron, you can see that its size has increased. It is due to the reason because now your same number of proton is applying force on a greater number of electrons, and also due to an increased electron, the repulsion has increased. So two reasons are there. First, there are greater number of electrons as compared to the proton, and second, there is more repulsion because of an increased electron. I guess this is clear to you. So it is seen that for the normal fluorine, the size is 99 picometer, and for the fluoride ion it is 181 picometer. Okay. Now next, so we have already defined what is your cation and what is your anion. Now, if we take a ionic crystal means you take your sodium chloride, which is your normal salt or your table salt. Just calculate the distance between the cations and anions, and that should be adjacent to each other. Similar to the case of metallic radii, they should be adjacent to each other, next to each other. Then half of the distance between these two is called as the ionic radii. Okay. Sorry, the distance between the cation and anion is called as the ionic radius. Now a very important point. What is the trend that is seen in the ionic radii? So this trend is similar to the atomic radius. So ionic radius follow the same trend as your ionic radius. A very important point which is related to ionic radius is your isoelectronic species. So what are isoelectronic species? From the word itself it is clear. Iso means same, electronic means electrons. So those species which have the same number of electrons are called as isoelectronic species. Now, this isoelectronic species can be used for the atoms, those have the same number of electrons, for ions, for molecules. So all of these three can be considered as your isoelectronic species. Suppose you take two molecules that have the same number of electrons, then also you can call them as the isoelectronic species. Similarly, if your two ions are having the same number of electrons, you can call as the isoelectronic species. So here is a list of 4 isoelectronic species: O2 minus, F minus, Na plus, and Mg2 plus. First is having 8 electron in the neutral state I am talking. Then in the second 9, in the third 11th, and in the fourth 12. Now what do? They go to the ionic state by gaining or losing electrons. Suppose your oxygen, neutral oxygen, gains 2 electrons and acquires a total of 10 electrons. Similarly, a fluorine gains 1 electron, sodium loses 1 electron, and magnesium also loses 2 electrons. Now, if they do this procedure, they all will have the same number of electrons. Therefore, they can be called as the isoelectronic species. So it's very important to understand this. that for the isoelectronic species, the ionic radius is inversely proportional to the integral value of charge. Now, moving on next. Here is a question for you. Which of the following species will have the largest and smallest size? 4 species are given here: Mg, Mg2 plus, Al, Al3 plus. Your time to solve this question starts now. So what will be the answer? Okay, your time is up. Let us see. So first of all, if I ask you, which one has the largest size? Which one of this will have the largest size out of all of this? So, I had said you that as you increase the charge, the integral value of charge, the size will decrease, right? So Al3 plus will be the smallest one in this. Okay, but what about the remaining two, Mg and Al? They are also present here. What about these two? Let us see the correct answer now. So the correct answer will be the Mg is the largest species. Which one will be the largest species? Your Mg will be the largest species. Yes. And what about the smallest species? It will be Al3 plus. Okay, it will be Al3 plus. I have said you, first of all, compare the charges, right? So Mg2 plus and Al3 plus have the largest size, largest charge. Therefore, they will be the smallest one. First will be Al3 plus and then the Mg2 plus. Now what about these two, Mg and Al? They both have the same amount of charge, which is 0. Now we know that what is the trend as we move across a period or we move down the group. Therefore, if you do that, you will find that the magnesium has the largest size because it is on the left side. Okay, it is on the leftmost side. Now moving on to the next question. Next part, which is ionization enthalpy. Now its definition is very, very important. Definition says that ionization enthalpy is the energy which is required to remove an electron from an isolated gaseous atom. Which type of gaseous atom? Isolated gaseous atom. And that gaseous atom should be in the ground state. Now, this is expressed always in terms of kilojoule per mole. So this is the, I would say, the standard way to represent the ionization enthalpy. Then it is always required to input energy to remove an electron. Therefore, your ionization enthalpy will always be positive. So two things are there. I would say three things. First, ionization enthalpy is calculated as the energy required to remove electron from the isolated gaseous atom. Second, it is expressed generally in the terms of kilojoule per mole. And third thing, it will be always and always positive. Now, this can be in multiple ways. If we are removing the first electron, then in that case it is called as the first ionization enthalpy, where it is represented here as del IH1. Suppose we have an element X and we are removing an electron. Therefore, it must be in the gaseous state. See, the state is given as G to maintain the definition that your atom should be in the gaseous state. Now we remove one electron and hence it will have a positive charge with a release of one electron. So this is the procedure, and the energy associated with this is called as the first ionization enthalpy. Similarly, if we remove one more electron from the same species and call it as the second ionization enthalpy, then it is represented by del IH2. This is shown here in the equation. Now again, your element is in the gaseous state, X plus gaseous, electron is removed, the element goes to the +2 oxidation state and one electron is removed. The next and the most important point is that your ionization enthalpy of second is always greater than the ionization enthalpy of first. Okay, that is delta IH2 is always greater than the delta IH1, because if you see in the second case, we are removing an electron from a positive species. X plus is a positive species. Now it has already a, you would say, scarcity of electron due to the positive charge. Therefore, it will be very difficult to remove the electron from this positive species, and hence we will require more energy. Therefore, the delta IH2 will be greater than the delta IH1. Okay, right? So the important point which you should consider in every of the equation, these of the equations, is that your species from which the electron is removed are in the gaseous phase. Now we will address the trend here. So the trend is very simple to address. It is opposite to that of the atomic radius. It increases as we go down the group, okay, and it decreases as we descend in a group, right? Descend in a group. So as we are moving across a period, it increases. As we go down the period, it decreases. So these are the 2 points, just opposite to the atomic radius. So this can be shown in this diagram. You can see that as we are increasing the atomic number, the atomic radius is first increasing, then it decreases. For hydrogen, which is before the helium, right? Just see the helium written here, and before that we have the hydrogen. So as we move from left to right, the ionization enthalpy increases. Again, as we move down the group, it decreases to lithium. Further, as we are moving from left to right, the ionization enthalpy is increasing, but there is a small exception in that. We will see to it in the upcoming slide. But generally what happens, as we are moving from lithium to neon, that is from left to right, the ionization enthalpy is what? It is increasing. Whereas if you compare lithium, sodium, potassium, rubidium and cesium, the ionization enthalpy is decreasing. Okay, you can see it clearly in the graph. I guess this point is clear to you. Now, what is the reason for this trend? As I have told you that your atomic radius and ionization enthalpy are inversely related. And what is the reason behind their inverse relation? Suppose you are considering an atom with a smaller radius, and now you are trying to remove the electron from that small radius. Due to its small size, it will be closer to the nucleus, and hence you will find it very difficult to remove the electron. Okay, therefore, as your size decreases, you have to apply more and more energy to remove that electron. Whereas if your size increases, it will go away from the nucleus, and you know electrostatic force of attraction is inversely proportional to the distance. Therefore, it will be easier to remove the electron in that case. Okay. Now there are exceptions in the trend. We have talked about it. The first exception is the ionization enthalpy of beryllium is greater than that of the boron. So if you see the periodic table, hydrogen, then helium, then lithium, beryllium and boron. So beryllium comes first and boron comes after that. Therefore, boron must have a higher ionization enthalpy, but it is not true. Instead of that, the beryllium which is coming first has a greater ionization enthalpy. And what is the reason behind it? Now most of the student makes a mistake of telling that since your beryllium has a complete filled 2s orbital, therefore it has a greater ionization enthalpy. So that explanation is completely wrong. Now what is the reason? The reason is that as you are removing the electron in case of beryllium, the beryllium outermost shell is 2s. So you are removing an electron from the 2s. And you know the penetration effect of 2s is very large. Hence it will be more closer to the nucleus and difficult to remove. Whereas in case of boron, the electron is present in the p subshell, which has a lower penetration effect. We have seen the penetration effect in the previous class in the atomic structure, and we know that p has a lesser penetration effect. Therefore, it is less closer to the nucleus and easy to remove. Now you will ask, why are we not considering the reason of full filled orbital in case of s? Because why are the full filled or half filled orbital subshells stable? Remember, the reason is the exchange energy. It can exchange its position. If you have seen it there, then you must have seen that the D has a comfort of exchanging its position, but it is not possible for the 2s, because in 2s subshell no more orbitals are present. It cannot exchange its position from any other orbital in case of 2s, because only one orbital is possible in case of 2s, right? Therefore, the reason of giving the fulfilled s orbital is completely wrong. Now the same can be seen in this trend. You can see that beryllium has an ionization enthalpy of 899, whereas your boron has an ionization enthalpy of 801. Now there is a second anomaly, which is nitrogen and oxygen. Now this nitrogen and oxygen can be explained on the basis of half filled or full filled, because its outermost electron is in the p subshell, and p subshell has more orbitals where it can exchange its position. The electrons can exchange its position. So what is the exception? That your ionization enthalpy of nitrogen is greater than that of oxygen, although nitrogen comes first. The reason behind it is that your 2p electrons are singly occupied in case of nitrogen. Just take the electronic configuration of nitrogen, it is p3, 2p3, right? Therefore, it is half filled and there is a chance of exchange from px to py and py to pz, and hence it is difficult to remove the electron in case of nitrogen as compared to the oxygen. Now again, this can be seen in the graph. Nitrogen has an ionization enthalpy of 1402 and oxygen has of a 1314. Now let us try to summarize all of this. What is covalent radius? It is half the distance between the two identical non-metal. Distance between what? Between the nuclei of the two identical non-metals that are bonded together in the covalent bond. Second point, metallic radius. It is half the distance between the nuclei of the adjacent metal atom in a metallic lattice. The important point is that your metal atoms should be adjacent to each other. Third point, atomic radius increases down the group and decreases across the period. What is ionization enthalpy? It is the energy required to remove an electron from the gaseous atom. Remember, the gaseous atom in the ground state. And your ionization enthalpy what happens? It decreases down the group and increases across the period, opposite to that of atomic radius. What are the key points that you should remember? The exceptions. So your atomic radii of metallic and covalent is not expandable to the noble gas because they are not present in the combined state because of complete electronic configuration. Second point, the first ionization enthalpy of boron is less than that of beryllium, and the reason was your last electron of boron was in your p subshell, whereas in case of beryllium it was in s subshell, and the penetration effect of s subshell is more. Third and the last point, the first ionization enthalpy of oxygen is less than that of nitrogen because of the half filled subshell in case of nitrogen. So I guess this is clear to you. So this was all for today's lecture. Thank you.